So, in this problem, we see you are driving north into an intersection with no stop sign. And at the center of the intersection, the car was struck by the other car that was traveling east. So we are traveling north, they are traveling east. The speed limit on both roads entering the intersection is 50 miles per hour. So both cars are set to 50 miles per hour speed limit. They skid together, they sort of hit and they locked. And they traveled 56 feet at an angle of 30 degrees north of east before stopping. So they hit right in the center of the intersection, traveled 56 feet at 30 degrees north of east. At the library, you determine the weight of your friend's car. His is 2,600 pounds. Your car is 2,200 pounds. And we are including the driver's weight, so that's total weight. It's good. The coefficient of kinetic friction for a rubber tire is 0.8. U sub k equals 0.8. It is not enough to prove that the other driver was speeding. You must also show that your friend was under the speed limit. So what we need to prove is that the car, your friend, traveling north. Sorry, we got these car weights backwards. 22 and 2,600. Your friend is traveling north. Your friend's car is 2,600 pounds. Your other car, the stranger, is going to the right at 2,200 pounds. And so we need to prove our friend was not speeding. That's really the goal. We don't need to prove that they were speeding. It's more that we're trying to prove our innocence in this, that it was not our fault at all. So how can we do that? Well, we can analyze the fact that we have these two cars. We can find their total mass. We can find the force acting on them while they skid, right? That friction force. And maybe we can find something valuable like their initial velocity, right? What we're trying to do is find a way to determine the initial y component of velocity, right? Because these two cars are traveling, they collide, they stick together inelastically. We're going to assume it's almost perfectly inelastic. They hit together and they just skid at the specified vector, 56 feet, 30 degrees north of east. Okay, so what we can do is analyze the conservation of energy. We know these two cars are traveling with a given kinetic energy, and that they sort of end here. And in order to apply the conservation of energy, we look from the instant they crash to the instant they stop moving. So when they crash, they have this kinetic energy, 1/2 m1 v1 squared plus 1/2 of the mass of the second car times the velocity of the second car squared, right? You can add them together. But we want to sort of look at the velocity of them together. And so we can find this new v, v12. And this is their combined velocity. And we can say that we have 1/2, and we're going to add the two masses together. Times v12, oops, not one, I2, 12 squared. What that means is we're looking at the instant they have inelastically stuck together. We have the mass total is both cars' mass added together. So we have 1/2 m1 plus m2. And then we're going to use their combined velocity, which is just sort of this vector. We are going to be talking in terms of magnitude for the most part. Just magnitude of v12, not really talking the direction. And so this tells us our initial energy. And we know that while we are skidding, all of this energy is converted into heat through friction, right? So we have work done by friction, right? So the force of friction times d, distance, right? That is our work done by friction. So the work done by friction is equal to the entirety of the kinetic energy. That friction loses all of their kinetic energy in the form of heat between the tires and the road, right? And so we can identify our force due to friction is mu sub k times the normal force, which is just m1 plus m2. And so we get 1/2 m1 plus m2 b12 squared equals mu sub k d m1 plus m2. And we know all these variables except for v12, which we can solve for. So one part of this that we need to be very careful of is that in the kinetic energy equation, we are looking at mass, so it should be divided by g. In reality, these m's should be w. Pounds are a weight, not a mass. And so we have to change all of these to be w. My bad. Thought we could get away with it. We couldn't. And so in the kinetic energy equation, we're looking at 1/2 mass times velocity squared. The mass is weight divided by gravity. When we look at the friction force, we're looking at the normal force, and forces in pounds. Pounds is a force. It's the weight, right? The weight is the force of gravity. The force of gravity is a weight. So when we look at our friction force, we are looking at just 2200 plus 2600. Right? That adds our forces. That tells us what force is pushing up, what the normal force is. But when we look at mass in imperial is actually slugs, which is pounds over g, right? Weight over gravity. We told us like slugs, which is our mass units in SI. We never really want to quantify that. We'll write it out as weight over gravity. And these weight terms will cancel, and we can find V12. So in order to figure out what speed each car enters the collision with, we have to apply the conservation of momentum to the x and to the y axis. So we look at V12 sine 30. This is our y component of the resulting velocity of the two cars. That times W1 plus W2 over G is our momentum, right? MV. The mass is weight divided by gravity, and the velocity is V12 sine 30. And that's in the y component, right? So this is our sort of final y momentum. That must be equal to our initial y momentum, which is the mass of your friend's car divided by g, the weight of your friend's car, times v of your friend. And so using this, we can find the velocity of your friend, right? This will tell us how fast he was going. And in this problem, just make sure you guys know if you're on the right track. Your friend should be in the clear.